good afternoon and or good evening for those who are in other time zones. I'm Ron Hawkins, Director of Industry Relations, and this is our November Technology Forum presentation. For those of you who've joined us previously, welcome back. And for those who are coming in for the first time, welcome. We try to do these about monthly. And the purpose is to showcase some of the research and education activities that we have going on here at SDSC that may be of interest to external audiences, as well as giving our industrial partners a chance to educate you on their technology and capabilities. So all with the intent of developing future collaborations and partnerships. So if you're new to this and you find value in it, we hope to see you online for future ones. So the company we have today probably needs no introduction for this audience, NVIDIA. They've certainly been the pioneers of using the graphics processing unit architecture for things other than video and graphics, including HPC and AI, and still the market leader in that, and have been in the news quite a bit of late with various acquisitions to, I guess, bulk out their technology portfolio. Companies like Mellanox, low latency networking, and ARM processors, which are the behemoth in embedded computing. So maybe one day we'll hear more about those things, but today we are here to hear about the next evolution or maybe revolution in NVIDIA's GPU architecture, Ampere. And we are fortunate to have Mark Hamilton from NVIDIA, Vice President of Solutions Architecture and Engineering, who's been able to carve out some time to take us through the Ampere architecture. And I look forward to that. I hope you all do. And without further ado, I'll hand it off to Mark.
Hi, thank you very much. And thank you for inviting me. In the pre-conference before we started, I was saying how I love to visit SDSC. I've visited many times, and I've seen many iterations of supercomputers in your, I guess, basement data center, though it doesn't really look like the basement when you walk in from the bottom. SDSC has been at the forefront of so many of the trends going on right now in supercomputing, right? We still have this infamous top 500 list, in Green 500 list that gets published twice a year. And SDSC has been one that for so many years, right, has focused on not just flops, but really how do you accelerate applications, right? And applications are all about I/O, data intensive applications. And today applications are not just about traditional simulation, but about combining data science with simulation, right? The laws of physics haven't changed, right? We're not, our roadmap does not anticipate the laws of physics changing, but our roadmaps do anticipate that you will simulate the laws of physics when you have to, and when you don't have to, you will fill in with data science. And we'll talk about some of the things. And so I know, many of the systems that SDSC has built, many of the experiments that run there have been focused not just on running HPL, but really achieving real science with the work that you do. So again, thank you for joining. Before we start, we're all doing this virtually, right? And I know that so many of us are maybe, working from home in less than ideal circumstances. My kids are grown up, not at home anymore, and so I don't mind. right? I haven't stepped on a plane since March, and I've got a lot of time, but I talk every day to employees and people who, they're working in a cramped apartment, their kids are running behind them trying to do daycare or school, and of course, all the people, right? SDSC has a great healthcare center. My daughter works is a doctor in pediatric intensive care, and so many days she's dealing with very sick kids who have COVID and other diseases. So to all the people that you know, to any of you that have been impacted directly or by your family, thank you. And it's amazing how much of the work of supercomputer centers around the world have turned around and reprioritized COVID research. It's also a great example of where simulation and AI are coming together. These sorts of visualizations of molecular dynamics are well known to anyone who's you can't walk in a supercomputer center and see some picture like this in the lobby or somewhere. And of course, what the supercomputer historically did was simulate, right? Laws of physics, laws of biology, right? Build up, from the molecular level, cells, DNAs, proteins. And today, what is happening is that's being combined with AI. And a perfect example is, right? You could simulate, how these protein binding interactions would work, but you can also, once you simulate it correctly and cross-check it in the real world, you can go through and teach an AI how to look at the early part of a simulation and decide if a protein is going to dock or not. And some amazing results coming out of that. And so hopefully the video plays here, little short 2-minute video talking about some of the work that NVIDIA's been doing.
Yeah, Mark, looks like the video may be consuming all the available bandwidth, but nice graphics.
It sounds like there's some problems with the video, so I'm gonna go ahead and skip through the video. But some of you may recognize the voice there. That was Abe Stern, who's one of our solution architects. I know he's been down to SDSC a number of times, and he recently took a new job at NVIDIA, and now he is our chief architect for our Clara genomics software development kit. I'll talk a little bit about Clara as we go, but San Diego, besides being the home of one of the most amazing supercomputing centers, is also a hotbed for life sciences, right? So many biotech startups, so many labs and divisions of big biotech companies. COVID-19 is really brought to the forefront the importance of this industry, but it's a tremendously hard one, right? $2 billion of R&D going into a drug. You spend $2 billion in over a decade, and you have a 90% failure rate, right? So that's $2 billion, and sometimes it's thrown away in over $1 trillion industry. And so if you look at how supercomputing is being used, right, it's being used across the whole pipeline, right? Or really starting with, this huge database of chemical compounds, searching for, potential candidates to dock, which the video was showing, starting at the genomic level, examining the structure, simulating at the molecular dynamics level. Again, many of the simulation tools, they're measured on nanoseconds per day that you can simulate, right? And so if you're only simulating at nanoseconds per day on a server, you need a lot of servers, you need a big supercomputer to simulate even a few seconds, right? And then of course imaging, right? No field has perhaps been earlier and more impacted by AI than computer vision in imaging. And finally, even things like natural language processing, conversational AI play an important role, helping search through the thousands, tens of thousands of papers published every year, combining that with real world data and using that as part of the drug discovery process. So where does NVIDIA play in this? Obviously, you'll say, well, it's with your GPUs. Your GPUs are accelerating a lot of the different parts, but so much of it is our software. Rapids is our software. The GPU accelerates data analytics, right? I think when my son went to school, he was a computer scientist, not a doctor. Is he used pandas, right, in his first data analytics class, and so Rapids has a GPU accelerated API that is compatible with pandas. I remember several years ago we were on vacation, and he had a friend visit, and she was starting the summer vacation, and so she was starting in the fall on her PhD in computational chemistry at a university on the West Coast. It wasn't UCSD. And in her background was computational chemistry, and she told I walked into the dining room table, and my son was showing her Python. I go, Evan, why are you explaining Python to her? And she said, oh, Mr. Hamilton, in order to start my PhD, I have to pass a test in Python, right? And I don't know Python, so Evan is being kind enough to explain Python to you. He was not explaining Rapids. This was about 3 years ago and before Rapids came out. Clara is our toolkit used in the healthcare and life sciences space. It ranges from Clara Parabricks, which is the leading GPU accelerated genomics toolkit, to Clara Imaging, and a number of new APIs. This is just sort of hot off the press. Senzio Bassini, who runs the Cenica HPC Center in Bologna, Italy. Italy's been in the news a lot this week about how they're shutting down basically the country, right? It's harder. You can't even travel from city to city now in Italy because of their second, third wave of COVID. And they have a consortium there. It's interestingly, ENI, Italy's leading oil and gas company, is part of this consortium. But they used a system that they have, Marconi 100, and Senzio was so excited. He sent me the email yesterday, and he said, we took down our system for 72 hours last weekend, and we ran a run on it. He said, we explored 7 protein sites. Actually, he said it was 6.5, because on the last one, the 7th protein, they only got 75% through. But they said they docked 475 billion ligands against these 7 protein sites. Again, looking at which of these proteins could be potentially a cure or a vaccine or otherwise support COVID-19 research. This was, he stated, and I haven't gone through the math, but he said this was 6 times more than has been accomplished on Autodoc on the Summit supercomputer at Oak Ridge National Labs. So again, they were very proud of that. Down in biomedical research, Microsoft and OpenAI was in the news because lately they talked about how Microsoft had built a 10,000 GPU cluster in Azure specifically for OpenAI. And OpenAI, of course, recently released their GPT-3 model, uses up to 175 billion parameters. A predecessor to that is Megatron, the Megatron AI model, and NVIDIA worked and created BioMegatron, basically a version of Megatron that is trained on a life sciences literature tool set. And now, again, is being used by many medical centers. And what we're seeing in industry after industry is really traditional simulation fusing with AI in data analytics. That the head of ECMWF, and I should have updated the slide with this, but he was quoted in HPC Wire or Next Platform this week, and did an article that said the future of weather processing, will finally slowly moving to GPU acceleration. And he said, future weather forecasts will not be possible without GPUs. Not only because they need GPUs to do the physical simulation, but again, think about it. If you know anything about weather forecasting, one of the hardest parts hardest physics of weather to simulate is the physics of clouds, right? And if you think of a cloud and the physics behind it, it's natural. Well, every day there's a lot of airplanes with cameras or overhead cameras fly over San Diego, right? The airport's right there, right? And why are weather sites simulating clouds over San Diego when they can go take a picture and actually tell if there's clouds or not using AI? There's a small startup in China. In 3 years ago, they released a toolkit for doing just that, taking aerial photographs and recognizing clouds. And they're using that to feed into the CAMS climate model, which is one of the big climate models used in China. SimNet is a NVIDIA toolkit for combining simulation with AI. We use SimNet to actually design the heatsink for our Ampere GPU. Ampere, our A100 version, first version of Ampere has over 50 billion transistors and can be 500 watts or more, all in a little postage size, well, a little bit bigger than postage size chip. And so again, what AI is doing here is you start doing some traditional CFD design, you pick some that look like they're working well, and then you train the AI model for that. And then the designer can, instead of having to design a heat sink, go run a CFD that takes a couple of days, literally as they're designing it, saying, can it be a little higher, can it be a little wider, do I change the physical materials of it? The AI can accelerate and say, well, no, this is a good design, this is a bad design. So it's amazing around the world how simulation and AI are coming together. So when you look at how you build a supercomputer today and what needs to be done inside a supercomputing center, a research center, a university, it's a lot more than just simulation, right? Of course, you do visualization, and NVIDIA GPUs have always been great for that and always will be. With our Rapids open source toolkit, of course, we're now accelerating all of that Python data analytics code. And so many different algorithms, from pandas to other k-means, other types of data analytics, now being able to run on the GPU just as simply as you can write Python code and run it on a CPU. AI, as we talked about, in cloud. Now, clearly, if you're at SDSC and you're building a supercomputer, you hope that people come in and use that supercomputer and don't go use GPUs in the cloud. But of course, at UC San Diego, at other universities around the world where PIs are that use the SDSC supercomputer, they may start by using the cloud, right? Every cloud now has our A100 GPUs in the cloud. We'll talk a little bit more about that. In fact, we were talking just before we started about the student cluster competition challenge that's going on right now is part of the SC20 virtual conference. And congratulations to the SDSC team. I hear they've done very well on that. It's being done entirely in the cloud, right? Every team has access to the same identical NVIDIA V100, our previous generation of GPUs in the cloud. And finally, edge streaming, right? This is an area where, normally you think of edge and you think of a little, little device like this, or even smaller, at the edge streaming some data, and you think, well, that's not supercomputing. But increasingly it is, right? I mean, inside here you have probably a $10, 4K imaging sensor, right? And other sensors even smaller, that when you combine billions of them, it is supercomputing, right? And you can't possibly do all of that processing in your supercomputer center in the cloud. That needs to move out, increasingly to the edge. And I think, again, one of the reasons for NVIDIA's success is that we've been able to work on all of these problems, right? 64-bit double precision simulation, mixed precision for AI, 8 or 16-bit, cloud computing, edge supercomputing down to 3 or 4 watt Jetson embedded GPUs, and able to do that all with one software platform, right? Again, building the GPU is today perhaps our easiest job that we have. But when you think about it, no other company today does everything from design a GPU, design the network with Mellanox, design the CPU, in the case of our embedded platforms with ARM, all the way up to designing supercomputers. And I'll talk about some of NVIDIA's supercomputers as we go. By being a full stack company, right, not only can we rapidly increase the performance, but on the left here, look at the V100 performance, right? If go back and look at the student cluster competition, I'm sure in 2017, I think it was used then. And but this is on a benchmark of about a dozen different applications. And we've run the same applications, same data sets from 2016 to today. They're listed in tiny print at the bottom so that we can have this apples to apples comparison. And the V100 GPU in 2017 was the same exact one as in 2019. And so you ask, how did you double the performance from 2x to 4x, the reference during that time? Well, of course we did it through software and improving our software. We have about 18,000 employees at NVIDIA today, and about 2/3 of them are software engineers. Only 1/3 are hardware engineers. In deep learning, of course, there's a well-recognized benchmark. It's not top 500, it's called MLPerf. It's actually a series of 16 benchmarks. And we run MLPerf today in about an hour on a big cluster, or we run top 500 in about an hour. The MLPerf benchmark takes about a month to go through and run and tune and optimize. It's so complex that only 2 companies submitted a full set of benchmarks. And one of them was the company that wrote the benchmark, which was effectively Google, and they came in number second, number 2. Sort of amazing that the company that writes the benchmark comes in number 2, but we love Google anyhow. They're a huge customer of ours. And again, they were one of the first to launch A100 in Google Cloud. So again, in the top 500, because again, it is a It is a reference. Again, it may not be the ideal reference to use, but it is a reference. And 8 of the 10 top 500 systems are accelerated by NVIDIA technology. Now let's look at exploding, data and model size. This is SDSC has for many years focused on data-intensive computing. When I go and look at your list of PIs and the different projects, so many of them are focused on data-intensive computing. And again, we use GPT-3, this language model from OpenAI, is sort of the benchmark for a large model for AI, 175 billion parameters. But there are so many data sets in the scientific world that are of equal size or greater. Just to give you some numbers, when we train the GPT-3 parameter data set with 175 billion parameters, we use 1,120 GPUs to do that. And that's what we call our DGX superpod. And it takes 61 days. The compute for it takes about 50 days, and it's 11 days to do the checkpointing, saving those 175 billion parameters every hour or two to storage. Because again, when you're using 1,120 GPUs, our GPUs are very reliable, but they're part of a server, and having that many servers stay up and running for 60 days, for 50 days, is not 100% reliability. And the cost, of course, of running for 49 days and then not having done a checkpoint and then having a server fail and crash your run is, of course, is very high. And so again, what we see, whether it's the design of the supercomputer or the design of software concepts like checkpoint restart, that for many years have been applied in scientific supercomputer centers like SDSC, we're now helping industry apply them as they build supercomputers for AI. And so this is the DGX SuperPod, right? We first built this internally for our own use. It may be surprising to hear, but NVIDIA has over 25,000 GPUs, over 2,500 DGXs that we use internally. It's not to run an NVIDIA cloud. We don't run a public cloud. These are our own researchers, right? And say, well, what are you doing, NVIDIA? You're not forecasting the weather. Well, no, we're not, right? But we are working on Clara genomics, right? That we talked about earlier. In that, we're working on autonomous vehicles. We're building the full autonomous vehicle stack for Mercedes-Benz in all of their cars starting in 2024. Even our gaming, right? Our gaming today features like a deep learning super sampling that let a gamer enjoy 4K level of performance with full ray tracing on an entry-level consumer class GPU is made possible by supercomputers like this running at NVIDIA, being trained on just basically playing computer games and learning how to recreate the images using AI without having to physically do all of the ray tracing. So again, we build this as a reference design. You see many of our partners here, and we can deliver the full system to you in your data center. We have all of the traditional OEM partners take the DGX reference design that we call HGX, and they build supercomputers out of it, all the way to even working with hosting companies that we've pre-qualified to host supercomputers like this. Here's the biggest one that we've built. Again, those 25,000 GPUs are not all in one cluster. Otherwise, it would be the world's fastest supercomputer on the top 500 list. But again, this is the biggest one we've built. We call it Selene, and it has several thousand GPUs, 280 DGXs, 2,240 GPUs. That seems like an odd number, right? It's not a 2,000, it's not a power of 2, and it's because we didn't just throw a bunch of GPUs together. The whole system down to the rack layout, down to the cabling, down to the InfiniBand fabric and topology is all designed by NVIDIA as a single product. So while a typical supercomputer may take 6 months or more to install, once we get all the piece parts here lined up, at the data center loading dock, we can go from a bunch of boxes in the data center to the supercomputer up and running in less than a month. And so with only 2,000 GPUs, only 280 servers, it's the #1 system on MLPerf. It's number 7 on the top 500. 280 servers and number 7 on top 500, and number 2 on the green 500. And next Monday, the top 500 list gets updated, and we might have some updates to this. But you'll have to check back on Monday. But we've turned this into a blueprint that, in effect, our customers can work with their favorite partner and get one. And so a number of customers around the world have. Argonne National Labs was one of our first customers. They've been in, it's sort of interesting, they've been in the news for they've purchased a different system that hasn't been installed yet. But when they received money to do COVID-19 research earlier this year, as the pandemic started, they reached out to NVIDIA, and they were actually our first DGX SuperPod customer, buying a SuperPod and installing it even before the launch. So they were our first customer, and we helped them be up and running with some of their COVID projects. CDAC in India. I know SDSC has research collaborations with India, because I've been at the high performance HIPC, High Performance India conference. It's usually held in December. It will be virtual this year as well. And I've been there and met SDSC folks collaborating. One of the systems we're installing actually right now is in Naver in Korea, Never. They are, in effect, the Google of Korea. They're #1 search engine, #1 recommendation engine in Korea. University of Florida, where our co-founder attained his degree, is installing a 140-node SuperPod. And the Wallenberg AI and Software Center in Sweden is installing a national resource in Sweden with the DGX SuperPod. And then finally, we announced a real interesting system that isn't a customer one. We announced what will be the fastest AI supercomputer in the UK, a system we call Cambridge One. This will be an extension of our internal clusters that we have around the world. So it'll be this is an NVIDIA system, owned and operated by NVIDIA. Again, primarily for internal use, but we've teamed with a number of the UK's leading healthcare companies, and we'll pick out select projects that they're not able to do yet, because they don't have a SuperPod, and we'll work with them to run some of those problems. So we're very excited. We're working hard to get this system built as we speak. And then around the world, many other A100 based systems have been announced. I know SDSC has announced a few systems that they'll be installing next year that will use our A100 GPU technology. So you'll be in good company and have a lot of great collaborators around the world. This is one of the slides that we'll show on Monday. A little bit of an advertisement. Monday at 3 p.m. California time, NVIDIA is holding a special event as part of SC20, and I really like that event because I'm the host of the event, but I don't have to present. So Ian Buck, who's the founder of CUDA, original developer of CUDA, is still at NVIDIA. Michael Kagan was the CTO of Mellanox and now is the CTO of NVIDIA for the whole company, will be my panelists, and they'll be speaking about some of the world's fastest AI supercomputers. One of them, just to highlight, the Jülich supercomputer. They'll be on the top 500 list on Monday. But just as far as measuring the AI flops, 2.5 exaflops of AI performance, peak performance. I did the math. It actually only takes 200 DGXs, 1600 GPUs, A100 GPUs to get 1 exaflop of AI performance. This is a system we announced several weeks ago. We talked about some of the work Chenik is doing on their current system with 3,200 V100s. Again, I guess besides the great work in COVID, they must have liked the system because as part of the Euro HPC initiative, they've announced the world's fastest AI supercomputer, 10 exaflops of performance, 14,000 roughly Ampere architecture GPUs, and they'll be installed in 2021 in Italy. So what we see here is this really interesting curve, right? At the bottom, we show the growth in HPL performance measured by the fastest systems on the top 500 list. And then the green line shows the projected performance of AI peak flops, right? And so the AI technology is advancing much, much faster. Now, again, it's a different measure, right? This is either bfloat 16 or FP16, take your pick. But again, the amount of research going into architectural design, it's not just because our chip implements bfloat 16, right? Google's TPU was actually, before we put bfloat 16 in Ampere, the TPU was the first to popularize bfloat 16. And they wrote the MLPerf benchmark, yet NVIDIA still leads it. So we're going to continue to increase HPL performance. In fact, one of the great things, and again, I know everyone was using for the student cluster competition was using the V100s, but the tensor core technology that was introduced in the V100 for 16-bit and 32-bit acceleration has now been extended to 64-bit tensor cores in FP16. Professor Satoshi Metsoko, who I know has been a collaborator with SDSC and is the director of the Riken Supercomputer Center, which runs Fugatu, the fastest supercomputer in the world. He was recently in HPC Wire talking about the importance of high memory bandwidth in matrix engines in the future of scientific computing. And the tensor core is in effect a matrix engine. This is a really interesting factoid, right? The first GPU in the cloud, the M2050, was 1 teraflop of AI performance, of FP16 performance. It's a little bit cheating calling it that because the M2050 didn't implement FP16, but if it did, right, it had FP32 and we doubled that, it would have been 1 teraflop. And last week, Amazon announced their P4D Ultra Cluster. P4D is the instance name, and you can go to Amazon today and get a cluster with 4,000 A100 GPUs. And it is, again, 2.5 million times the performance in 10 years in AI. Pretty amazing. And again, the question is, what are those workflows? How can you use that 2.5 million X increase in performance? If you're only running simulations at FP64, right, you're going to be on that lower performance curve. But researchers around the world have figured that out. As mentioned at the start, NVIDIA has announced their acquisition of ARM. It isn't completed. These big acquisitions take a year or more. I think we said we take about 18 months to do it, and that was a couple months ago. So we have a few months to go. But ARM is the leading computing CPU provider for embedded devices, right? Mobile devices. There certainly are ARM CPUs in the data center. Amazon has them. They last week announced some great performance specs on their ARM CPU. The world's fastest supercomputer, Fugatu, is built out of a Fujitsu ARM processor without any GPU. And we believe that what this combination will do is really, bring the age of AI to ARM, right? Why shouldn't the world's most popular CPU enjoy the benefits of NVIDIA GPU acceleration? So at the International Supercomputer Conference back in June of 2019, we announced that we're bringing the full NVIDIA CUDA platform to ARM CPUs. And in December or November at Supercomputing last year, we released the beta of CUDA on ARM. And then in April this year, when we launched the A100 Ampere GPU and introduced CUDA 11, we had full ARM support in CUDA 11 for ARM CPUs. So we're really looking forward to the combination, and again, having CPU technology, GPU technology, networking technology, and being able to optimize the software stack across all of those will be really interesting. And with that, just the networking, there's a big change going on in networking in the way you build supercomputers. You probably haven't realized this, but you'll be hearing more about this from NVIDIA next week. And again, we have some really interesting plans. GPU Direct RDMA. This is a technology that supercomputer centers that they use GPUs have known for years, and lets you accelerate communication from GPU to GPU. Newer, it's still in so-called early access, but this technology has been sampled for over a year now, since SC last year, is GPU Direct Storage. It provides that same concept of RDMA, but all the way from the storage to, in effect, the file system to the GPU. So again, a set of different technologies that extends GPU Direct RDMA all the way out to storage. And finally, our Sharp in-network computing. Initially, Sharp 1.0 helped accelerate MPI primitives by running the MPI primitives in the network. And now Sharp 2.0 plays a key role in our ML perf performance, right? We estimate, depending on the AI benchmark, but Sharp running in the InfiniBand network can provide a 15 to 20% speed up, basically 15 to 20% speed up for free. So again, here's a picture of our software stack. Again, at the lowest level is, of course, our GPU and our networking topologies, the CUDA platform on top of that, CUDA-X libraries, and then our different application platforms for different use cases. But what's changing, right? What's changing is the DPU, really being able to bring cloud-native supercomputing, cloud-native infrastructure to the supercomputing platform. What a DPU basically is a network interface. We show our latest ConnectX-6 here. This combined with different application engines, right, and programmable ARM cores, right? And you say, well, why would you do this, right? I already have ConnectX-6 today. Isn't that enough? Well, it isn't, right? Think about the way you build a supercomputer today is on the left, right? What runs on the server in the host CPU? Applications, your communication frameworks, MPI, etc., your storage software, management software, right? It used to be, what was the first thing that you did when you installed a small cluster, right, at the university? You turned off all the management. Well, that was okay if you have 8 systems networked together, by a grad student. But when you're running, a campus-wide supercomputer, you need management. And then, of course, you had your InfiniBand engine and adapter and your InfiniBand switch underneath. So our architecture for cloud-native supercomputing using a Bluefield DPU is, again, taking all of those parts in purple. They don't need to run on the host CPU, right? By taking those off and offloading them into the DPU, it does a number of things. First, with the end of Moore's law, right, the CPU is no longer speeding up, right, as much as it used to, but you still need the CPU, right? The CPU is super, super important. And so you want to save every last core cycle on the CPU for doing the jobs it has to do. Things that don't have to be done by the CPU, you want to offload, right? Parallel computing to the GPU, and these sort of, system management types of tasks to the DPU. And finally, by putting it in the DPU, right, it provides additional levels of security. And of course, the key here, right, is that anyone can build a DPU, just like anyone can build a GPU, right? NVIDIA doesn't have a monopoly on GPUs, but what differentiates the NVIDIA GPU from others is, CUDA, introduced in 2006, right? So, 15 plus years of application acceleration. Well, DOCA is the equivalent of CUDA for the DPU, right? It's an SDK that abstracts out, the different security, telemetry, storage, networking primitives that are accelerated by the DPU, and lets the application take advantage of the DPU. So again, that could be used to accelerate your storage, right? Instead of having, NVMe drives locally, you can in effect have remote NVMe drives. You can provide protected enclaves and additional security, right? By taking, in effect, isolating the host with the DPU. You can accelerate performance, right? Again, in a sense, the ConnectX-6 is an early example of a DPU. It doesn't have a general purpose ARM core on it, but it does have acceleration primitives on it. And so again, we think that this is, really the start of a new generation of supercomputers. So in our GTC, GPU Technology Conference, several weeks ago, Jensen announced our DPU roadmap. Bluefield 2 is shipping today, and he announced the roadmap going out to Bluefield 4 out in the 2022-23 timeframe. So again, I didn't repeat that here, but we're very excited about that. So with that, I've got about 10 minutes left for questions. And so let me stop sharing here and bring up the chat.